Welcome to Two Projects. In this video, we are going to explain the project Epileptic Seizures Prediction using Transfer Learning. Introduction. This project aims to utilize deep learning techniques for the prediction of epileptic seizures. By leveraging advanced neural network architectures and transfer learning methods, we seek to develop models capable of accurately forecasting the onset of seizures in individuals with epilepsy. Epilepsy is a neurological disorder characterized by recurrent seizures, often with unpredictable timing and severity. Predicting seizures in advance can significantly improve the quality of life for patients by enabling timely interventions, reducing the risk of injury, and providing peace of mind for both patients and caregivers. The ability to anticipate seizures also offers opportunities for personalized treatment approaches, ultimately leading to better management of the condition. So, the beneficiaries of this project include individuals living with epilepsy, their caregivers, and healthcare professionals. Patients with epilepsy stand to benefit from improved seizure management strategies, reduced anxiety associated with unpredictable seizures, and enhanced safety. And deep learning coupled with transfer learning plays a crucial role in this project by enabling the extraction of complex patterns and features from diverse datasets such as electroencephalogram, that is EEG recordings, patient medical histories, and environmental factors. Transfer learning allows us to leverage pre trained models on large datasets, thereby accelerating model training and improving performance even with limited labeled data. Objective of the project. So, as I mentioned earlier, the primary objective of this project is to develop and evaluate multiple deep learning models, including combination of CNN and SVM, VGG16, DenseNet 121, MobileNet V2, and exception for the prediction of epileptic seizures. These models will be trained on diverse datasets comprising EEG recordings, patient demographics, and other relevant features. Another objective is to conduct a comprehensive comparative analysis of the performance of each model based on key metrics such as accuracy, precision, recall, and F1 score. By systematically evaluating these metrics, we aim to identify the algorithm that demonstrates the highest predictive capability and robustness in seizure prediction. And the objective involves designing the seizure prediction system to be user friendly and accessible, ensuring that patients, caregivers, and healthcare professionals can easily interact with and interpret the results for informed decision making and intervention. Requirements needed to execute this project are software requirements. Software needed is Anaconda. Primary language used is Python. Front-end framework used is Flask. Backend framework used is Jupyter Notebook. Database used is SQLite 3. And front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Now we'll discuss the working modules of law of work. So the first step is import required packages. In this step, we import essential libraries such as NumPy, Pandas, sklearn, and TensorFlow Keras. These packages provide functions and tools necessary for data manipulation and neural network construction. The second step is exploring the dataset. Here we conduct exploratory data analysis to gain insights into the dataset structure, distribution, and characteristics. EDA involves tasks such as summarizing key statistics and identifying missing values. The third step is visualization. So, visualizations like count graphs help in understanding the distribution of different classes in the dataset, while time versus amplitude graphs of EEG provide insights into the temporal patterns of brain activity. These visualizations aid in identifying potential patterns and trends that may influence model performance. The next step is data pre-processing. So this step involves preparing the dataset for model training by handling missing values and scaling features to a consistent range. So data pre-processing ensures that the input data is clean, standardized, and suitable for training machine learning models. The next step is train and test split. In this step, the dataset is divided into training and testing sets to assess the model's performance on unseen data. Typically, a portion of the data is reserved for training the models, while the remainder is used for evaluating its performance. The next step is training and building the models. So multiple deep learning models, including combination of CNN and SVM, VGG16, DenseNet 121, MobileNet V2, and exception are trained using the training dataset. For CNN plus SVM, CNN extracts features from the data, which are then fed into an SVM classifier for classification. The other models are pre-trained architectures fine-tuned on the dataset. The next one is performance comparison. Here, the performance of each model is evaluated using metrics such as accuracy, precision, recall, and F1 score. These metrics provide insights into the model's predictive capability and effectiveness in distinguishing between normal, that is interictal, and predictal, that is seizure states. In the next step, a user interface is developed using Flask with SQLite for user sign up and sign in functionalities. This front end allows users to interact with the seizure prediction system. So, after signing in, users input test data, typically EEG recordings, into the system for prediction. This data is processed and fed into the trained models to classify whether the brain is in an interictal or predictal state. Finally, the system provides the predicted state of the brain, indicating whether it is normal or indicating an impending seizure. This information can be crucial for patients, caregivers, and healthcare professionals to take appropriate actions and interventions. Now we'll understand about the algorithms used. So the first algorithm built is combination of CNN and SVM. So the CNN plus SVM algorithm combines convolutional neural networks, that is CNNs, for feature extraction with support vector machines, that is SVM, for classification. CNNs extract spatial patterns from input data like EEG recordings, while SVMs classify these features into interictal, that is normal, or preictal, that is seizure states. This hybrid approach utilizes CNN's hierarchical feature learning and SVM's robust classification, making it apt for predicting epileptic seizures by effectively capturing complex patterns in EEG data and making accurate classification decisions. The next algorithm built is VGG16, that is Visual Geometry Group 16. So it is a convolutional neural network architecture consisting of 16 layers, including convolutional and fully connected layers. It utilizes small convolutional filters and max pooling layers for feature extraction and spatial reduction. VGG16 is chosen for its effectiveness in image classification tasks and its ability to extract complex features from EEG recordings, making it suitable for this project's objective of predicting epileptic seizures by leveraging pre-trained weights and fine-tuning on the dataset. The next one is DenseNet 121. So it is a convolutional neural network architecture characterized by densely connected layers, promoting feature reuse and efficient gradient flow. Each layer is connected to every other layer in a feed-forward fashion, enhancing parameter efficiency. In this project, DenseNet 121 is selected for its ability to extract intricate patterns from EEG data efficiently, aided by its dense connections. Its pre-trained weights facilitate transfer learning, making it suitable for effective utilization in limited seizure data scenarios. The next algorithm is MobileNet V2. So it is a lightweight convolutional neural network architecture optimized for mobile and embedded vision tasks. It utilizes depth-wise separable convolutions to reduce computational complexity while maintaining performance. With its efficient design, MobileNet V2 is ideal for applications with limited computational resources. In this project, MobileNet V2 is selected for its suitability in real-time seizure prediction, offering a balance between computational efficiency and predictive accuracy for deployment in resource-constrained environments. And the last one is exception. So exception is a convolutional neural network architecture that utilizes depth-wise separable convolutions to improve computational efficiency in image classification tasks. By separating spatial and depth-wise convolutions, it reduces the number of parameters while maintaining performance. In this project, exceptions, efficiency, and ability to extract intricate features from EEG data make it a suitable choice for seizure prediction, where both accuracy and computational efficiency are essential considerations. Now we'll see the comparison graphs. So this is the bar graph comparing accuracy scores of different algorithms. In this graph on x-axis, I have algorithm names, And on y-axis I have accuracy scores. Accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. This is precision scores comparison graph. In this graph on x-axis I have algorithm names and on y-axis I have precision scores. Precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. This is recall scores comparison graph. In this graph on x-axis I have algorithm names and on y-axis I have recall scores. Recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And this is F1 scores comparison graph. In this graph on x-axis I have algorithm names and on y-axis I have F1 scores. F1 score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for classifications, and we can see CNN plus SVM is doing well in all the performance metrics, so we will deploy it in Flask. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is dataset folder in which I have CHP-MIT dataset, which comprises EEG recordings from pediatric epilepsy patients vital for research in seizure detection and prediction. So we will use this data to train the models, and this is test data which contains test cases on which we'll make the predictions. This is models folder in which I have model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. This is static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML pages. This is Notebook Jupyter source file, which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file Explorer. I'm copying it. Open Anaconda prompt. So now use the command cd followed by space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost, and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a login link, click on it. So here we have to provide a credentials, username and password to login. And if we are new to the system, we have to register ourselves first. Click on sign up link, fill in all these details and click on register button to sign up. As I'm already a member, I'm clicking on the sign in link. I'm giving my credentials here and click on login button. So it has redirected us to the classifications page. So here we have to upload the test cases consisting of EEG recordings, and the application will classify the test cases as either interictal, that is normal, or preictal, that is seizure state. Click on choose file button. So I'm uploading the test data file. Click on open. The file is loaded. Now click on upload button. So we can see these are all the test cases I have and these are the predictions. So we can see the application has classified this test case as preictal state, that is seizure. It has classified this test case as interictal state, that is normal. So similarly, we can upload any test case and can get the classifications as either predictile or interictal. Now click on sign out. So the conclusion here is, throughout this project, we developed and evaluated multiple deep learning models for the prediction of epileptic seizures. Leveraging advanced neural network architectures and transfer learning methods, we aim to provide accurate forecasts of seizure onset to improve patient outcomes and enhance quality of life. We constructed and trained various deep learning models, including combination of CNN with SVM, VGG16, DenseNet 121, MobileNet V2, and exception, using EEG recordings and patient data. Each algorithm was fine-tuned and optimized to capture intricate patterns in the data and make accurate predictions. Among the models evaluated, CNN plus SVM emerged as the top performing algorithm, demonstrating superior performance in accuracy, precision, recall, and F1 score. Its ability to effectively extract features from EEG data and classify seizures with high accuracy makes it the optimal choice for clinical applications. And the integration of CNN plus SVM into a Flask framework allowed for user-friendly testing and real-time seizure prediction. Users could input EEG data and receive immediate results, empowering patients, caregivers, and healthcare professionals with timely information for decision making and intervention. So, the beneficiaries of this project include individuals living with epilepsy, caregivers, and healthcare providers who stand to benefit from improved seizure management strategies and personalized treatment approaches. Moving forward, there is potential to expand the system's capabilities, integrate additional features such as predictive analytics, and further optimize algorithms for enhanced performance and usability in clinical settings.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.